find the equation of the sphere centered at the point 5, comma, -7, comma, that's interesting. Anyway, sorry, 0 with a radius of 8. So this kind of problem is meant to be pretty straightforward. You just really want to toss these pieces of information into the standard sphere equation. So generally your sphere equation is like x minus the x coordinate squared plus y minus the y coordinate squared plus z minus z coordinate squared equal to the radius squared. So here we're just going to get x minus 5 squared plus y minus -7 squared plus z minus 0 squared equal to 8 squared. And if I was actually writing this as an answer to some question, I would probably do the very, very minimal amount of simplification here, which is to write this as x minus 5 squared plus y plus 7 squared plus z squared equal to 64. Right? Like it's not a lot, but it does seem reasonable to expect someone to do that. The part of this question, though, that I actually wanted to kind of address was, now let's ask the following question. How do I want to say this the right way? I was looking for the piece of paper that had the language on this specifically, but fine, I'll just make it up. So what, I can't think of the right word, curve, function, relationship, what curve do we get when we intersect this sphere with the plane x equal to 3? Now, this might seem like a challenging question, but it's really not. When you're intersecting a surface with another surface, in this case with a plane, all you have to do is substitute in x equal to 3 wherever you see 3. Or sorry, wherever you see x, apologies. So all we're going to do is we're going to take this equation for the sphere and plug in 3 for x. So if we plug in 3 for x, we're going to get 3 minus 5 squared plus y plus 7 squared plus z squared equal to 64. I'm going to do a little bit of simplifying to help us see what this new equation actually kind of translates to graphically. 3 minus 5 squared is 4, right? -2 squared, positive 4. And then we subtract that from 64. So I'm going to get the equation y plus 7 squared plus z squared equal to 60. And what we want to recognize here, and we think about what, so if you think about what happens if you take a sphere and you slice it with a plane, or like if you take an orange and slice it with a knife, what kind of shape do you get when you slice the orange with a knife? Like, that's not a good question. What kind of, like, if you look at the part that's actually sliced, that sliced part looks like a circle. Exactly. And that's what you get when you slice a sphere with a plane. The surface you would get if you look at that top surface is a circular surface, which is exactly what this equation is. Y plus 7 squared plus z squared equal to 60. This is a circle centered at, well, x is 3. So 3 comma -7 comma 0 with a radius of square root of 60. Graphically, here's kind of what it looks like we've done. We've taken this sphere, and I've chosen the wrongest plane to try and graph. You've taken your sphere and you've sliced it to, I don't know, left of center, right? If you're thinking about slicing it like this way out towards you, right? Because that's what x equals, well, no, x equals 3 would be this way. That's terrible. That's what, so I guess I could try. So like basically, right, here's my center. I'll try and draw this in a not terrible way. And then I've kind of cut it like out here in front of the center. So kind of done this. Let's pray that it turns out not terribly here. Let's see what happens. Go up this way. Gonna be kind of like, oh man, it's already looking dicey. I have bad vibes about this. That'll be fine. So here's kind of the smaller circle you get. Yeah, it's not my best work ever. Sorry. Here's the smaller circle you would get if you cut the orange in front of the center, or basically anywhere off center. So, long story short, if you're intersecting a surface with another surface like a plane, all you do is plug in the equation for the one thing into the other, if it's relatively easy to. A harder example of this would be like, what if we intersected this sphere with the plane y equals x? You'd still do the same thing. You would just substitute in x for y, and then it'd be a little funkier, but you'd still have something circular. Kind of weird. Any questions about that? Let's do one more that kind of gets at this, because there's another question on your homework that I thought looked. Oh, actually, there's two more things. Let's look at this one first. Let's say we had for z equal to x cubed plus sine of y to the fourth times x. Is that going to work out all right? Yeah, it'll be fine. Yeah, is that going to work out? I'm trying to think if I picked something terrible, I'll be fine. Sure. Find the rate of change in z at the point, sure, 0, 2, 0. Yeah, that'll be fine. Sure, it'll be fine. Sorry, the times you make things up. It's like the numbers are probably going to suck, but it'll be all right. Find the change in z at the point 0, 2, 0 as we change x but hold y fixed. So the thing they're asking us to do here is not hard. The thing that's hard about this question is understand what they're asking you for in the first place. So they're asking us to find the rate of change in z at some point as we change x but hold y fixed. What are they actually asking us to find? Let me make it slightly easier. Which partial derivative are they actually asking us to find? Right. Well, except I would call it zx in this case because I haven't called anything after. But yeah, you could say we're going to find what I would call zx, or if you prefer, del z del x. Either one's fine. But they're definitely asking us to find that because they're saying we're changing x and holding y fixed, right? That's the kind of magic words that are like, oh, we're changing x and holding y fixed. That means we're doing the partial with respect to x. So then we're going to do it, and we're going to get 3x squared plus the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff, which is just going to be y to the fourth. Because the derivative of x is 1. That's the partial derivative anywhere, but now we want to find it specifically at the point of interest. So we're going to take del z del x. Wow, that's really looking good there. And we're going to plug in the point. I prefer to write it like this. We're going to plug in the point 0, 2, 0. But you might see it written as del z del x, like at. They might even leave off the z part since z is a function of x and y. They might write it as like del z del x at 0, 2, or they might write it as zx at 0, 2. I don't love that notation personally, but it's totally fine. So then we're going to take our partial derivative and plug in 0 for x and 2 for y. So we're going to get 3 times 0 squared plus cosine of 2 to the fourth times 0 times 2 to the fourth. 3 times 0 squared is 0. Cosine, let's see, 2 to the fourth times 0 is also 0, and cosine of 0 is 1. And 2 to the fourth is 16. So we end up with 16. It did work out. I was worried I was going to be plugging in some number into the trig function that was going to be awful, but then I was just like, we'll make something 0 and be fine. So yeah. Okay, let's look at one more that kind of combines both of these first two questions. Let's say, Sorry, I keep meaning to number things as I do this, just to like make it easier to see what's going on later when I try to like write things down. Cool. All right. The plane, it's a plane. No, it's not that kind of plane. The plane y equals 1 intersects z equal to x to the 9th plus 5xy minus y to the 6th in some curve. All this first sentence is saying is you get a curve when you intersect this plane with this surface, which is typical when you intersect a plane with the surface. You get some curve in 2 dimensions. Find the slope of the tangent line of this curve at the point P equal to 1, 1, 5. So I guess you don't even have to do that. I was thinking, although I think it's worthwhile. So we're going to plug in y equal to 1. So our curve, when y equals 1, which is where we're living in the plane, y equals 1, is going to be z equal to x to the 9th plus 5x minus 1. All right, we're just throwing y in there. And even though they haven't explicitly stated it, if we're trying to find the slope of the tangent line of this curve at this point, we're going to be taking the partial derivative of z with respect to the only variable that's left, x. Now I should point out, maybe I should point out, we didn't actually have to plug in y equals 1 here to do this, right? We could have totally just taken the partial derivative with respect to x and then plugged in all the point at the end. And I'll kind of show you that in a minute. But here we're just going to take the partial derivative. We're going to get 9x to the 8th plus 5. And then we're going to plug in our point. So del z del x evaluated at the point 1, 1, 5. We're just plugging in the 1 for the x's. So we're going to get 9 times 1 to the 8th plus 5, which is really just 9 plus 5, which is 14. The reason I bring this up is because there's a few questions on your homework like these last couple questions, and I just felt like the language was not super duper clear right off the bat. So this should help you see what's going on with those questions. To kind of look at this a different way, if we just went ahead and took the partial derivative without plugging in y equals 1, so if we just started with taking del z del x, we would have gotten still 9x to the 8th. The partial of 5xy would just be 5x. And the derivative of y to the 6th would just be 0. And then when we plug in, well, there's still, it's interesting. This one's interesting because there's, I made a mistake. You guys know what it was? It would be 5y, right? So I made a mistake, right? Okay, 5y. Cool. So then if we plug in x equal to 1 and y equal to 1, we still get the same result. So if we plug in del z del x at the point 1, 1, 5, we still get 9 times 1 plus 5 times 1, which is 14. So technically, if you're trying to find the slope of a tangent line in a particular direction as on some plane, you don't have to plug in that plane first, but it's probably easier to do so. So yeah. Okay, let's find the other things. Yeah. You're good. Not what I want though. Yeah, let's do that. So let's talk about finding and classifying relative extrema. And I can't remember which one we did last time. So I'll just pretend like we didn't do whichever one we're going to do. So let's start with this one. I know it's a different problem. So let's say we have the following function. F of x comma y equal to x cubed minus 3xy plus y squared. And let me see one thing here. They have no, it's fine. Okay. It's all right. So to find critical points, you're just finding where both the first partial with respect to x and the first partial with respect to y are equal to 0. Because like I talked about last time, I don't know, Reed, did you watch the video from class? From last? It's all right. It's still fine. I was just curious. Basically, the idea is if you're trying to find where you have a maximum or a minimum, you're kind of looking at, well, where I'm kind of looking for the top of this mountain here. And the top of that mountain, the tangent plane is horizontal. And if the tangent plane is horizontal, both the partial derivative in the x direction and the partial derivative in the y direction, those are both going to equal 0. And the same is true whether you're finding a maximum or a minimum. Not that they always look like this, but these are just easy to draw. Or even, and this is the fun one. I do like drawing this one. I'm gonna lie, it's kind of fun. Wow. I mean, if maybe it's a lie. I don't like drawing this one anymore. Sorry, I used to like drawing this one when I knew how to draw it. My God, yeah, saddle point. So right there, that saddle point. You have a minimum in one direction and a maximum in the other direction, but still both those derivatives are equal to 0. So each one of these shapes has a horizontal tangent plane, or a tangent plane that is parallel to the floor, to the XY plane. And again, the way we find those potential critical points, just like in 17A, just like in 16A, when we find critical points by taking the first derivative and setting it equal to 0, it's the same idea. It's just we have to find points where both of these first derivatives are equal to 0. So let's do it. Let's find fx. It's going to be 3x squared minus 3y plus 0. Probably, yeah. Gum, nice.
Flashbacks of high school.
Yeah, I bet he was putting gum under desks. Interesting. And the partial respect to y is going to be 0 minus 3x plus 2y. Everyone's at 0. Now I will point out, to me, this one is a little more challenging than usual, in that often when you're solving these, you just kind of get a point right off the bat. Here, we're not going to get any points right off the bat. We actually have to take one of these equations and sub it into the other one. So I'm going to take this first equation here. Say, well, I've got 3x squared equal to 3y, divide both sides by 3. I've got x squared equal to y, or y equal to x squared. And then I'm going to take that, and I'm going to plug it in for y here into the other equation. So here I'm going to have negative 3x plus 2 times x squared equal to 0, which I might rewrite as 2x squared minus 3x equal to 0, and then factor out an x. I'm going to have x times 2x minus 3 equal to 0. So here are my two potential x values. I could get x equal to 0. I could get x equal to 3/2. Now that's not the whole story, right? Because to find a critical point, it has to have an x and y coordinates. So I'm going to go back over here and say, well, okay, if x is equal to 0, y is going to equal 0 squared. So I'm going to get the point 0, 0. And if x is equal to 3/2, y is going to equal 3/2 squared, which is 9/4. So I'll get the point 3/2, 9/4. And the point of these points is that both of these points should satisfy both of these partial derivatives equal to 0 at the same time. If we plug in 0, 0 here, yeah, 0 minus 0 is 0. Plug in 0, 0 here, yeah, 0 plus 0 is 0. If you plug in 3/2, 9/4 here, you're going to get 3 times 9/4 minus 3 times 9/4, which will equal 0. If you plug in 3/2, 9/4 here, you're going to get negative 3 times 3/2 plus 2 times 9/4, which will cancel out to equal 0. So both of these points make both of these equations 0 at the same time. Okay. How do we figure out if they're maxes or mins or something else? Yeah, but so it's kind of like, it's actually the second derivative test. So back in, So back in 16A, 16B, I don't remember. Back in whatever class we learned how to do this, right? We learned that you could show that a function has a minimum, not by showing like it goes from decreasing to increasing, but by showing that the second derivative is positive, right? For example, we can tell that, I'm going to make it real straightforward. We can tell that f of x equal to x squared minus 2x. If we take the first derivative, we get 2x minus 2 equal to 0. X equal to 1 is our critical point. And then instead of doing the first derivative test and seeing that the function is decreasing and then increasing, we can do the second derivative test, seeing that the second derivative is positive, which means that no matter what point we plug in, but specifically plugging in the critical point, it's positive. And that second derivative being positive means this critical point gives you a minimum because you're at the bottom of your being concave upness. Well, there's a similar test for functions of two variables. So we're going to do, of course, I've given myself not enough room. No, I should not try to squeeze it in here. We calculate a thing that is similar to this second derivative, except it's called capital D, and is equal to the second partial with respect to x times the second partial with respect to y minus the mixed partial squared. It's called D because it's the determinant of the Hessian matrix. If you really care, nobody cares, but that is why it's called capital D. Now, it's not just like for no reason. What was that? Oh, really? Did you call it delta? F working. Oh, interesting. Huh. All right. I've never capital gamma. Oh,
He was like, your text calls it D, but I call
capital
it
gamma, like that?
Yeah.
Weird. Okay. We can call it capital gamma. I've never heard of that before. In any event, you calculate, so you have to calculate all the second partials. Well, not all, you have to calculate almost all of them, except you don't have to calculate the mixed partial both ways. Last time we did talk about how the mixed partial is the same thing for normal functions. There are examples of functions that are weird and defined piecewise, where the mixed partials actually don't work out to be the same, depending which direction. But those are few and far between as far as we're concerned. And I don't think we ever run into them in this class. So as far as we're concerned, fxy equals fyx, we're good to go. So looking back at our function here, well, in fact, looking back at our first derivatives, our second partial with respect to x is going to be 6x minus, oops, you can't see that, 6x minus 0. Our second partial with respect to y is going to be 2. And our mixed partial fxy is going to be, well, if we take the partial of x with respect to y, I'm going to get negative 3. I kind of like doing a little check and seeing if I did fyx, do I get the same thing? And I do. If I do the partial derivative of fy with respect to x, I also get negative 3. So that's good to see that that's happening. So then we calculate capital D. Capital gamma, apologies. Calculate capital gamma of x comma y, and it's equal to fxx times fyy minus fxy squared. So we could simplify it. Yeah, we could simplify this. This is equal to 12x minus 9. So if we plug in 0, 0, right, because that was one of our critical points. Capital, God, I don't like drawing capital gamma at all. Capital gamma of 0, 0 is going to be 0 minus 9, which is negative 9, which specifically is negative. We'll talk about this in a second, but when you have negative ones, that means we get a saddle point. So this means 0, 0 is a saddle point. So whenever capital D is negative, the point you plugged in to get that negative value gives you a saddle. And then if we plug, sorry, I'm going to keep saying capital D. I'll try to say gamma, but it's, a lot of years of doing it a different way. So capital gamma of my other critical point, which was 3/2 comma 9/4. So we're plugging 3/2 in for x, and we're getting 12 times 3/2 minus 9. which is equal to 36 over 2, which is 18 minus 9, which is positive. We don't really care what the value is. We just care whether it's positive or negative. So when it's positive, that means, it really means you have to do a little more inspection, but it means we could have a maximum or a minimum. And the way we check is by checking the second derivative with respect to x or with respect to y. Because here's the thing, and this is kind of neat to see. If this quantity is positive, these two things had to have been the same sign. Because if these were opposite signs, then this would be negative, right? And fxy squared is positive, so a negative number minus a positive number is just going to be more negative. So the only way for this to not be negative is for sure to have had fxx and fyy be the same sign. Which means we only have to check one of them, right? Because if we know they're the same sign, once you know one of them is positive, you know the other one's positive. So if gamma is positive, then we look at fxx or fyy to see if that second derivative was positive or negative. So looking at fyy, we see that fyy is 2, which is positive, which means we're concave up, which means we have a minimum. So a minimum at the point 3 halves comma 9/4. There's something else I wanted to say here. I feel like, oh, we could have also plugged in. So for fyy, we didn't even have to plug in, right? Because the second derivative was just always 2. But if we had plugged into fxx instead, fxx at the point 3 halves comma 9/4 is just going to be 6 times 3 halves, which is 9, which is certainly positive as well. So you can check either one, and if you're looking for a max or a min, once you know one of them, you know both of them are the same sign. Okay, so here is the general idea. Gamma is equal to this fxx times fyy minus fxy squared. And we have essentially 3 things that can happen. Thing 1, if gamma is negative, then we have a saddle point. If gamma is positive, then one of 2 things can happen. If fxx or fyy is positive, then it's concave up, which means we have a minimum. On the other hand, if fxx or fyy is negative, then we have concave down, which means we have a maximum. And sadly, much like the second derivative test of your, if this thing that we're calculating is equal to 0, the test is inconclusive. We don't know. That doesn't mean it's not possible to figure out what we've got. It just means that this test won't tell us. For example, if I look at the function f of x comma y equal to x to the 4th plus y to the 4th. Well, let's find the critical points. So what's the partial with respect to x? Pretty straightforward. Set that equal to 0, you get x equal to 0. And the partial with respect to y is similarly for y cubed. Set that equal to 0, you get y equal to 0. So our critical point is the point 0, 0. Let's calculate gamma, which I will never really think of as gamma. So fxx, fyy minus fxy squared. Let's see, so fxx is going to be 12x squared. And fyy is going to be 12y squared. And fxy is going to be 0. I usually don't find it to be in my interest to simplify this expression. You might sometimes, but generally it's not. If we plug in our critical point, we get 0 times 0 minus 0 squared, which is 0, which is inconclusive. However, you could probably make a pretty convincing argument that 0, 0 is a minimum. Because x to the fourth plus y to the fourth, if you're plugging in anything except for 0, 0, you're going to get a positive result. So this is a minimum because f of x, y is bigger than 0 for any other point. Sometimes people ask about stuff like that. Not a lot, but sometimes. Now let's look at some more examples here. I like this example. I don't love this. Yeah, that's a good. Yeah, I like this example. So my examples might be more complicated than the ones you'll see in class or on your homework. There's only one of these questions on your next homework assignment where you actually have to find critical points. All the other stuff is like domain, range, finding partial derivatives, finding second partial derivatives. So yeah, but it's never a bad idea to get ahead. So let's look at another example here. Yeah, let's look at this one. Let's say we have f of xy equal to 3x cubed plus xy squared minus 9x squared minus y squared. I want you to define both of your partials. While I look for something. I thought I had a thing like that. If you found the derivatives, you can start trying to find the critical points, but they're a little challenging. Oh, that's the example I found last time. Okay, that's cool. Okay, I'll grab some easier examples here in a minute. So our partials, 9x squared plus y squared minus 18x, or set that equal to 0. And then we're also going to have, what is it? 2xy minus 2y equal to 0. So rule of thumb, deal with the easier looking thing first. So of these two, the second one definitely looks easier to try to figure out. So I'm going to do that. Specifically, if I'm trying to solve 2xy minus 2y equal to 0, what can I factor out? Right. If I factor out a 2y, I'm left with an x minus 1. So I either get y equal to 0 or x equal to 1. I want to be super duper extra clear about this. 1, 0 is not a critical point. If you plug in 1 for x and 0 for y, yeah, fy will equal 0. If you plug in 1 for x and 0 for y up here, it will not equal 0. If you plug in 1 for x, you get 9, and you plug in 0 for y, you get 0. So 9 plus 0 minus 18 definitely does not equal 0. So if I make that extra clear, because I've seen a lot of students being like, oh, I got an x and a y, that means it's a critical point. It's not. It means these are the values that make this 0, but not necessarily this. What we do with this is we take each of these and then we plug them back into this, because we definitely know to find a critical point, either y has to be 0 or x has to be 1. No other values are going to make fy equal to 0. Great. So let's take this and first plug in. Let's plug in y equal to 0. Let's plug in x. Sure, y equal to 0. Doesn't really matter what you have to do both of them. So plug in y equal to 0. I'm going to get 9x squared minus 18x equal to 0. And then I can factor out a 9x. I'm left with an x minus 2. So I end up getting either x equal to 0 or x equal to 2, which means I have the critical points. Well, y was 0, so I've got 0, 0, and 2, 0. Those are both critical points. Okay, now we're gonna do the same thing for x equal to 1. So for x equal to 1, I plug in 1 for x, I'm left with 9 plus y squared minus 18 equal to 0. Solving that, let's see, 9 minus 18 is negative 9. I get y squared equal to positive 9. So I get y equal to plus or minus square root of 9, which is plus or minus 3. So I get 2 more critical points here. X is 1 and y is 3, and x is 1 and y is negative 3. Those are my 4 critical points. You could plug any of these critical points into both of these partial derivatives and get each of them equal to 0. Okay. So now we have to calculate gamma for each of these 4 points. So let's just calculate gamma first of all. So I would probably over maybe here. Yeah, let's give ourselves some room. Just off to the side, I'm going to calculate fxx. That's going to be 18x minus 18. I might factor out the 18 here to make it easier to see what things are going to look like. If I look at fyy, it's going to be 2x minus 2. Does that seem right? Yeah. Which again is something times x minus 1, which is interesting. And finally, fxy is going to be 2y, I think. Yeah. Is fyx also 2y? It sure is. Yes. Great. Cool. So now we can find gamma. I don't like drawing. So gamma is equal to fxx times fyy minus fxy squared. Cool. And again, I don't think it's to our interest to really multiply this out because we're just going to plug in points to see what happens. So let's start with the easiest one. Let's plug in 0, 0. We plug in 0, 0, we're going to get 18 times negative 1 times 2 times negative 1 minus 0 squared, if you like. 18 times negative 1 times 2 times negative 1. I don't care that it's equal to 36. I care that it's positive. Okay, so it's positive means we have what? No, it doesn't. Gamma being positive only means you have a maximum or a minimum. Concave up specifically depends on each of the second derivatives on their own. So when you see gamma being positive, you should think I have more work to do. Gamma positive means we have to do a little bit more work. Yeah. I feel like I had a good picture of this. So one of the things to think about here is, how do I say this the right way? Basically, gamma being negative kind of means that essentially your 2 second partials are opposite signs. So you kind of have one being concave up and one being concave down, so that you have a saddle. Whereas gamma being positive essentially has to mean that both partial derivatives, second partials of x and of y, are the same sign. So they're both going concave up, meaning you have something that looks like a minimum, or they're both going concave down that looks like something's a maximum. But really, gamma is more to help us find the saddles because really, well, let's see. We'll see a saddle in a second. We'll talk about it. But let's just, so this one here could be a max or a min. But then we look at the second derivative and we see that, oh, fxx was negative because it was negative 18. And it being negative means the thing's concave down, which means we have a maximum. So we know that 0, 0 is a maximum. What else do I want to say about this? No, nothing. Let's look at the next one. Let's look at 2, 0. So gamma of 2 comma 0 is going to equal, let's see, plugging in 2 for x and 0 for y. So I'm going to get 18 times 1. I'm not even going to write the 1 times 2 times 1 minus again 0 squared. That's clearly positive. So now we look at the sign of either fxx or fyy, and we see that either one is positive, meaning we have a maximum or a minimum.
Minimum.
Right, we have a minimum. So we know that 2 comma 0 is a minimum. Okay. If we look at gamma of 1 comma 3, we get 18 times 0 times 2 times 0 minus 2 times 3 squared. That's a whole lot of 0 minus something, which means it's going to be negative, which means you automatically have a saddle point. So it's weird here, right? Because like we have partial derivatives or second partial derivatives that are both equal to 0, right? So meaning like at the saddle point, it's not really, you can't really talk about like the concavity in either direction. So it's kind of just funky. So that's kind of what I think of gamma doing, is it helps us account for maybe you're not really looking at this thing in the right direction. Yeah, let's finish on and then we'll talk about another example in a second here. Yeah, right. I think that's right. Yeah, sure. Okay. Let's look at the last one here. I think it's going to be the same. We plug in 1 comma negative 3. We're going to get again 18 times 0 times 2 times 0, which is 0 minus 2 times negative 3 quantity squared, which is still going to be negative. So again, we have a saddle. So what I'm trying to say, not very eloquently, or I'm trying to say it eloquently, but not doing a very good job, is that functions are funky. If you look at something like f of x, y equal to x times y, I think that's what I want. Let's graph it. So there are some nice graphing utilities. I like GeoGebra, although I found a new one. I kind of like it. It's all right. Graphing. This one's pretty all right. Sometimes it gets funky, but it works just fine. It's nice to see things every once in a while. If we graph z equal to x times y, maybe. Ooh, yeah. So look at that saddle. Let me zoom in, maybe. So, I mean, it's helpful sometimes, but it's kind of giant, right? Ooh, yeah, okay. So you can kind of see the saddliness, maybe. Yeah, saddle. You can even add one. Shift it up a little. Yeah, maybe it's easier to see the saddliness now. I mean, it's called a saddle because it literally looks like a saddle, right? Like, I often think of it as like ungraciously as like the crotch of your pants. That's also what it looks like, because one part goes like this, one part goes like this, right? That's kind of also what's going on there. But this function is kind of interesting because this one here is not like your usual way I think of a saddle. Like my kind of general typical saddle, everyone's favorite saddle equation, is usually f of xy equal to y squared minus x squared. That one, it's super duper clear to see, oh, we are going, if I let x equal 0, I've got z equals y squared. It looks like this. And if I let y equals 0, I've got z equals negative x squared, which looks like that. And then we can kind of try to not draw it terribly. Whoops. But you don't say those things until you've drawn it. There's our saddle. Fun times. And definitely saddle, right? If we take, fx is -2x, set that equal to 0, you get x equal to 0. Fy is positive 2y, set that equal to 0, you get y equal to 0. And then fxx is -2, fyy is positive 2, and fxy is certainly 0. So your gamma is -2 times 2 minus 0 squared, which is -4 always. And so since that gamma is negative, for sure at your critical point, you're going to get a saddle. Oops. That time it's right. And we can kind of see here, oh yeah, it's very obvious that, in the x direction, it's concave down, and the y direction, concave up. Whereas with this function here, I feel like it's a little bit less obvious. If you find fx, it's going to be y, set that equal to 0, you get y equals 0. Find fy, you get x, set that equal to 0, you get x equal to 0, and that's kind of silly. And then if you take the second partials, fxx is, it's 0. Fyy is also 0. Fxy is 1. So here our gamma is 0 times 0 minus 1 squared, which is just -1. So it's still also concave down, or not, sorry, not concave down, still a saddle point, but it's just a little weirder. So I've probably not done a great job of explaining why this gamma thing works the way it does, but essentially you're subtracting off this fxy to account for, do we have things kind of going in the same direction or not? Are the concavities of x and y both kind of the same way or opposite ways? I know it probably could be said better, but that's the best I've got today. Do we have time for one more? Kind of not. Sure, let's look at one more. Grab this back over here. Or not. Maybe we'll just. Yeah, we can look at one more quick example here. Let's say we had the following. Let's say our function was f of xy equal to 2x squared minus y squared plus 4x plus 6y plus 1. This example, I would say, is a little more, probably more likely what you're going to see in 16C, where we want to find and classify all critical points. So fx is going to be 4x plus 4, set that equal to 0. Fy is going to be -2y plus 6, set that equal to 0. And here it's nice. We just get one critical point coming out. We've got 4x equal to -4, x is -1. We've got -2y equal to -6, y is equal to 3. Since those are the only things that solve each equation, our critical point is the point -1, 3. And then plugging it into the gamma is not so terrible. In fact, well, interestingly here, so fxx is going to be 4, fyy is going to be -2, and fxy is going to be 0 squared. So gamma everywhere is equal to -8. So gamma at this particular point, it feels kind of silly, but there's nowhere to plug in the -1 and the 3, right? We just get gamma of -1, 3 is -8, which is negative. So we have what? Saddle point. Saddle all day long. So it's kind of the hard part about these particular problems, in my opinion, is finding the critical points. This one's relatively easy. The one we did before was a lot harder. Finding the critical points is kind of the challenging part. classifying them is just memorizing a thing. Right, so you have to memorize if gamma is negative, saddle point, if gamma is positive, what do we get? More work, exactly the answer I was looking for. We get to do more work. We look at one of the second derivatives and see if it's positive or negative to determine if we have a minimum or a maximum. But it's kind of right, that's the process. That's it. Yeah, that's all I got.